Hello there, this is a geometry video. It is chapter 8, section 1, and we are starting a new chapter here. And so today we'll be talking about the geometric mean. The geometric mean is when means of a proportion are the same number. Now you've seen proportions before. Here's an example of a proportion, but what I wanted you to notice with this diagram is that we have the extremes are here in case you didn't remember what we call this. The product of the means is equal to the product of the extremes. Did I say that twice? Product of the means is equal to the product of the extremes, which we'll call the cross product property, which you learned a long time ago how to solve proportions. But at any rate, if you don't remember, these are the means right here and to the extremes. And so in this case, the means are denoted by the same variable x, because we're trying to indicate that they're the same number. So when that happens, you have what they call the geometric mean. So again, this is for a and b being positive numbers, a and b are greater than 0. But if you were going to solve this using the cross product property, you would go x times x, which is x squared, and then a times b. And then you would square root both sides. And so you have a little formula, which is x equals the square root of a times b. Basically, we use this formula as the geometric mean. And so we're now going to do an example with this geometric mean. Let's find the geometric mean between 8 and 10. Now, if you want, you can set the proportion all over again, but because we already came up with the formula for it, all we want to do is say that x equals the square root of a times b. So in this case, 8 times 10, which is then the square root of 80. And then, of course, we want to break down the 80. 80 can be, let's see, 20 times 4, but I think that 4 goes into 20 as well. So I think we want to go 16. So my calculator is out of battery there. So 80 divided by 16 is 5. So 16 times 5 is 80. And the square root of 16 is 4. So x equals 4 root 5. That is the geometric mean of 8 and 10. So now you can try the same thing. You can also figure out approximately what that's equivalent to. 4 root 5 is approximately 8.9. Alrighty, so you can go ahead and find the geometric mean for a and b. And then we're going to go to our theorem for today. We actually use the geometric mean. The geometric mean brings us to these theorems, which are all about right triangles and altitudes. So if you remember, the altitude of a triangle is the segment that extends from a vertex to the opposite side at a 90-degree angle. So what I want to do right now is I want to kind of explain what you're already seeing on the board here. I went ahead and wrote it ahead of time, so save video time. But you're probably wondering, what in the heck is all of that? The first thing I want to do is draw in the altitude to this very first triangle. So we had triangle ABC, and I am drawing the altitude because it says here in the theorem, it says if the altitude is drawn to the hypotenuse of a right triangle. So you start off with a right triangle, which is triangle ABC, and then you draw in the hypotenuse, you draw in the altitude, which is the segment that goes from a vertex to the opposite side, which happens to be the hypotenuse, at a 90-degree angle. Okay? Like that. When that happens, then the original triangle, which is why I wrote here original, the original triangle ABC is basically split and creates two more triangles. So now you have two triangles here. You have a large triangle, so to speak, and a small triangle. So you have this triangle here and this triangle there. So again, what I've done is I've kind of pulled it out of the diagram so you can kind of see over here. We have from A, so we'll mark this from A to D to C. That's the left of the original triangle. And then you have CDB, which is the right. And so I've pulled them out there so you can kind of see them. But basically, when you draw that altitude, to the hypotenuse, then the two triangles that are formed are similar to the original. So the large triangle is similar to the original triangle, and the small triangle is similar to the original triangle, and also they are similar to each other. So what I want to do right now is I want to write out these similarity statements. Again, it looks very crazy right here. And so what I've done also is in the original triangle, in the diagram, I kind of color-coded the different segments of the triangle. You remember that there's a long leg, a short leg, and the hypotenuse leg in a right triangle. So here's my short leg, my long leg, my hypotenuse leg. And same thing over here, there's the long leg, the short leg, the hypotenuse leg. And same is true for the small triangle over here. I've also labeled the triangles. This is my original triangle. This here represents the large triangle, and then that there is the small triangle. And one of the things that you will notice is that we have to, you know that when you have similarities, then the sides are in proportion to each other, and that's going to come next. But before we can get to that, we need you to be able to write what is similar to what. How do I write this? So what I'm going to do is I'm going to say triangle ABC. Okay, we said that the original triangle is similar to the large, the original triangle is similar to the small, and then the large and the small are similar to each other. Okay, so what I want to do right here is how do I write the statement? So ABC is basically going from hypotenuse to the short leg to the long leg. So when I write the large triangle's letters, they have to be in the right order. So I'm going to go in the same order, hypotenuse, short leg, long leg. That means I'm going to go hypotenuse, short leg, long leg. So I'm going to go A to C to D. That's important because it means that angle A corresponds to angle A, angle B corresponds to angle C, and angle C corresponds to angle D in the respective triangles. So it's pretty important that you do that. We also know that the original triangle, so here we're going to say original triangle is similar to the large. We'll abbreviate there. And we also know that the original triangle, which is ABC again, is similar to the small triangle. We'll abbreviate SM for small. So again, we're going the same order here, hypotenuse, short, long. So in the small triangle, I need to go hypotenuse, short, long. So that would be hypotenuse, short, long in that direction. So it's going to be C, B, D. All right, so those are my first two similarity statements, which basically state that the original triangle is similar to each one respectively, but also we know that the large triangle is similar to the small triangle, according to this as I am to each other. So again, we're just going to keep in the same spirit of what we've been doing, hypotenuse, short, long. So if we go hypotenuse, short, long, that's going to be triangle A, C, D. And over here, hypotenuse, short, long is C, B, D. So those are the three similarity statements that we get from this theorem. So now we want to do our example. And it says, write a similarity statement identifying the three similar right triangles in the figure. So one of the first things that you probably want to do is to write, if you want, you can reposition the triangles so that you can see them better. You don't have to do that, but it is useful. So you can identify the different legs, otherwise it can get kind of confusing. But here we have F, G, H, and so if I want to pull out the blue triangle, it's going to be like so. The 90-degree angle is J, and then the short leg is going to be F over here, so FJ is the short leg, and then G is over here. So we have GJF, GJF. And then if I take the other triangle here, the red triangle, nice and color-coded here, the right angle here of the red triangle is J, and then we have the short leg is G, so GJ, so we need GJ, and then the long leg is GH, I'm sorry, the long leg is JH. This is the hypotenuse. The hypotenuse is GH. So there's H, and this is my hypotenuse, and this is my long leg. So now you have all your triangles. So what I'm going to do now is I'm going to come over here and say this is my short, this is my long, and my hypotenuse. This is my short, my long, my hypotenuse. This is my short, my long, and my hypotenuse. And why do I do that? Because I need to come up with 3 similarity statements. So the first one is going to be the original to the small, the original to the large, and then to each other. So the original triangle, I'm going to go FGH, triangle FGH. So in that order, I'm going short, long, hypotenuse. So I'm going to go short, long, hypotenuse. So I'm going to go in this direction, short, long, hypotenuse, FJG. I also need to do the same thing for the larger triangle. Okay, so again, I'm going to go FGH, which is short, long, hypotenuse. So over here, short, long, hypotenuse is going to be GJH. Just like that. And then my last similarity statement is going to be the small and the large similar. So again, we're going to go in the same order of short, long, hypotenuse. So short is going to be FJG. So I'm going short, long, hypotenuse. And then short, long, hypotenuse is going to be GJH. And those are the 3 similarity statements that I needed to come up with in this little guy. Alrighty then, so now, if you will do these do-it-yourself examples, we are going to go on to what I was talking about earlier. Once you know that 2 triangles are similar, then we learned in the previous chapter that their corresponding sides are in proportion. So we have 2 more theorems. They're related to the geometric mean. They're theorems 8.2 and 8.3, but they have special names, so I'm going to go ahead and call it geometric mean of the altitudes, and then in the next slide you'll see the geometric mean of the legs. Now you will not find this information, at least not in this format, in your textbook. They use different letters to indicate things. I just think it can get really confusing when you have all this diagram or all these different sides going on. Now the reason why we have a geometric mean is because what you're going to notice in these triangles is that they have shared sides. And when they have a shared side, that means that the 2 proportions are going to have the same means. And so I've indicated that in the diagram here with that orangish diagonal. But I kind of want to show you what I'm talking about. Again, I've reproduced these triangles just so that I can have it on this page. If you already have it in your notes and you can refer to it quickly, then you don't have to keep rewriting it, because I'm going to write this again in the next slide. But I do that so that I can refer to it while I'm talking to you. So again, I've just reproduced the large and the small triangles. I've kind of given them names so that you can set it up later and it'll be easier if I've color-coded the segments. But what you'll notice is that the short leg of the original triangle happens to be the same as the hypotenuse of the small triangle. And you can see that here, this is the small triangle. So this leg here is the hypotenuse of this small triangle, but in the original triangle, it's the short leg. Same is true for the long leg. The long leg of the original triangle also happens to be the hypotenuse of the large triangle. So again, when I'm saying these terms, the original refers to ABC, the large refers to the left, and the small refers to the right. So the long leg of the original triangle is the same as the hypotenuse of the large triangle. And then also, we know that the hypotenuse here of the original triangle ends up being a combination of the long and short legs of the respective other triangles. And so all this information we're going to try to set up the corresponding parts because we know that corresponding sides should be proportional. So we're going to start first with the altitudes, and that's when we compare the large triangle to the small triangle. So we're not using the original triangle at all. We're comparing the large triangle and the small triangle. So that's why I put here, I rewrote this. We already said this in the previous slide, that triangle ACD, this time we're going hypotenuse, short, long, is the same as hypotenuse, short, long, so CBD. So we've kind of rewritten that here. And now I have here on this side of my proportion, I'm using segments from the large triangle. And on this side of my proportion, I'm using segments from the small triangle. And what we know is that we want to go long leg to short leg of the large triangle and long leg to short leg of the small triangle. Well, the long leg of the large triangle is AD, so I've written that there. The short leg of the large triangle is CD. But at the same time, the long leg of the small triangle is also CD. And so you kind of see that geometric mean thing happening there. And the short leg of the small triangle is BD. So this is your setup. So you've got AD is to CD as CD is to BD, and they're the same. Okay, so it's important that you set that up correctly. Then we have two more proportions for you. And those are the geometric, this is Theorem 8-3 now, the geometric mean of the legs. So in the previous slide, we were comparing the large triangle to the small triangle. Now we're comparing the large triangle to the original triangle, and then the small triangle to the original triangle. All right, so again, I've rewritten the similarity statement here, and we've got large to original, just like we did before. And so in the large to original case, you want to compare the hypotenuse to the long side. Hypotenuse to the long side. So the hypotenuse of the large triangle, right here is the hypotenuse of the large triangle is AC. So I've written that there. The long leg of the large triangle is AD. And then we have the hypotenuse of the original is AB. And the long leg of the original, which we said earlier, is AC. And so again, you have this geometric mean happening because these are the same segment. Okay, then we compare the small to the original. And in the case of the small to the original, you want to go hypotenuse to the short leg, hypotenuse to the short leg. So the hypotenuse of the small triangle is BC, and the short leg of the small triangle is BD. Then the hypotenuse of the original triangle again is AB, and the short leg of the original triangle is BC, and so there you see again that BC is a shared side, and therefore you have your geometric mean. I do believe that if you have this diagram and you compare the sides, hypotenuse, long leg, short leg, it'll make it easier for you to do the homework. So we have an example here where it says find x, y, and z, and of course you can tell this is a right triangle where the altitude is also split to right triangle, so it creates two triangles, and so you can see that you have a small triangle. Here we have a small triangle, a large triangle, and of course the original triangle. We are given the hypotenuse of the original triangle because we have the length here is 20 and the length here is 5. So we have the hypotenuse of the original triangle, and we have the long leg of the large triangle, and we have the short leg of the small triangle, which is 5, and then we've got to figure out all these x, y's, and z's. So what we need to do is set up a bunch of proportions. So we're going to go ahead and start with the altitude theorem, which I've now, I don't want to keep going back and forth, but I do have it here written down on some paper here. The altitude theorem is going to compare the large triangle to the small triangle. So we want the long to short. We want to compare, let's not make this too big. According to your notes, if you have them from the previous slide, you want to go from long leg to short leg. Long leg to short leg. And you want to compare the large triangle to the small triangle. Okay, so I go to the large triangle, which is right here, and I'm looking for the long leg, which I know is 20. And then the short leg is going to be x. And then in the small triangle, the long leg is x, and the short leg is 5. And just like that, I've set up my proportion. I can solve for x, because x times x is x squared, and hence you get the geometric mean going on. 20 times 5 is 100. Sorry, don't know why I'm having a brain fart there. And you get that x equals 10. Once we know that x is 10, we can now go on and try to find the other values as well. So let's go ahead, and I'm going to write in here that this is 10 now, where the x was. Okay, and so now we want to go ahead and set up another problem. And so now we want to do not large to small, because we've already figured all that out. But we want to go from the original to the large, and then you want to go from the original to the small. Okay? So when you go from original to large, you want to compare hypotenuse to the long. And when you go from original to small, you want to compare hypotenuse to short. Okay, so here we go. In the original triangle, the hypotenuse is 25, because we're going to combine both of those together. So 25 here and 25 there. In the original triangle, the long side is 20, and the short side we just found out is 10 from our previous, from that previous part there. And then we want to go to the large triangle. In the large triangle, the hypotenuse of the large triangle is z, and the long leg of the large triangle, we already said, was, hypotenuse to long, large triangle is, hypotenuse to long is 20. Thank you. Over here in the small triangle, you want to go hypotenuse, which is going to be y, and then the long side, the short side, which is 5. Okay? So we're going to get 20z is equal to 25 times 20. 25 times 20, let's see here. Oops, battery dead there. 500. Divide that by 20, and you get that z equals 25. And over here, you're going to get 10y equals 25 times 5, which is going to be 125. Divide that by 10, and you get that y is equal to 12.5. And I want to make sure that I did that correctly. I'm just checking my work here. Original to large is hypotenuse long. Original to small, hypotenuse short. Original triangle is right here. Hypotenuse of the original triangle is 25. The long leg of the original triangle, oh my goodness. I'm so sorry, I did this backwards. I'm so glad that I caught that though. I knew something was off, I just didn't know what. And y'all probably already noticed and just couldn't tell me. So I'm sorry, I was doing the wrong sides. For original long, the original long side is actually z, that should be here. And then the large hypotenuse is going to be z as well. That makes more sense. And for the long side of the original, of the large triangle, it's 10. I am so sorry. Let's correct that real quick. We got that, and that means that I probably did it wrong over here too as well. So, Okay, let's do this again really quick here. Just to recap, in case you missed that, for the original triangle, the hypotenuse is 20 plus 5. For the long side of the original triangle, that's here, z. For the hypotenuse of the large triangle, that's going to be z as well. Hypotenuse of the large triangle here, opposite 90 degrees. And then the long side of the large triangle is the 20. So there we go. Now for this guy, we have the hypotenuse, again, is still 25 for the original triangle. The short side for the original triangle is actually y. And then the small triangle, the short side is 5. And in the small triangle, the hypotenuse is also y. So now we should get y squared. And here we're going to get z squared, and that makes more sense. That's why I was thinking that something was wrong, because I didn't see the geometric mean happening. Glad we picked up on that. So 25 times 20 is 500. We already knew that. And then we want to square root that. And that's going to be 100 times 5. The square root of 100 is 10, so it's going to be 10 root 5. 500, which is approximately 22.4. And then over here we're going to get y squared. This is 25 times 5 is still 125. Only this time, when we do the square root of 125, you actually get approximately 11.2. 125 is going to be 25 times 5, so it's going to be 5 root 5. The exact answer is 5 root 5 and 10 root 5, or approximately 22.4 and 11.2. All right, so now that's correct. So sorry, so see, it's very confusing sometimes if you're not making sure that you have the right segments. So please use those diagrams that I provided for you. So right now we're going to have this do-it-yourself example for you. And once you have completed this example, you will have completed your notes for this lesson, and I will see you in class. And thanks for watching.